Hello everyone, welcome to my channel Chemistry by ANR. Today we are going to start with the unit Biomolecules. Biomolecules is a unit which deals with carbohydrates, then we can say types of carbohydrates and all these. We are also going to deal with amino acid, proteins, their structure, but we are going to do it in parts. So carbohydrates are hydrates of carbon. They have the general formula, molecular formula as CxH2O whole Y. But it is not essential that all compounds having this general molecular formula or fitting into the formula will preferably be a carbohydrate. There are some exceptions which we are going to deal with. Now, we are going to study as monosaccharides, disaccharides and polysaccharides. What are they? Monosaccharides are those compounds, those carbohydrates that cannot be further hydrolyzed into simpler units. Disaccharide means those carbohydrates that can be hydrolyzed to obtain two monosaccharide units. Further, we are going to deal with reducing sugar, non-reducing sugar, sugars, non-sugars, and so on. So let us explore new concepts. As I said, that carbohydrates are hydrates of carbon that have the general formula as CxH2O whole Y. That means compounds that fit into this can be named as carbohydrates, but it is not essentially always occurring. Why? Because acetic acid CH3COOH can fit into this formula. See, we can write C2, then we can write H2O whole say twice. But it is not a carbohydrate. We all know acetic acid is not a carbohydrate. There are certain carbohydrates like rhamnose having this formula C6H12O5. Okay, but it is a carbohydrate that cannot be represented as CxH2O whole Y. So in general, we can say carbohydrates are optically active polyhydroxycarbonyl compounds, aldehyde or ketone. What does it mean? By the term optically active, we know that they are capable of rotating plane polarized light. That means they have a chiral center. So they are optically active. The meaning of the term polyhydroxy means many OH groups attached. Many OH groups attached. Carbonyl, that is, they may have an aldehyde linkage or ketone. So they are optically active polyhydroxy aldehyde or ketone. If it is an aldehyde, it is known as aldose. If it is a ketone, it is named as ketose. Now, those carbohydrates that are sweet to taste are sugars, and which are not sweet to taste are non-sugars. Okay, so we can see that sweet to taste cellulose, non-sugar glucose, non-sugar that is not sweet to taste can be cellulose. Again, aldehyde, that carbohydrate having aldehyde group can be named as aldoses, and having keto group can be named as ketoses. This table shows that the general term triose, if it is a ketone, then ketotriose. If it is an aldehyde, then aldotriose. And what is the meaning of this term triose? It actually means this carbohydrate or this monosaccharide contains 3 carbon atom in total. Tetrose mean containing 4 carbon atom in total, be it aldehyde or ketone. If it is an aldehyde, then it will be named as aldotetrose. If it is a ketone, it will be named as ketotetrose. Now, aldehydes, carbohydrates can be categorized as monosaccharide, disaccharide, oligosaccharide, polysaccharide. What are they? Now, based on how many products that are obtained on hydrolysis of the carbohydrate, you can classify them as monosaccharide, oligosaccharide, or polysaccharide. Like monosaccharide means it is the simplest form. You cannot hydrolyze it further into simpler units. About 20 monosaccharides are known in nature. So they are naturally existing monosaccharide, 20 in number. Glucose and fructose we are going to study. Ribose is another example. Oligosaccharide means these carbohydrates on hydrolysis, they produce 2 to 10 units of monosaccharide. So they can be a disaccharide, they can be a trisaccharide, tetrasaccharide, so on, but not more than 10. If it is more than 10, then it is a polysaccharide containing greater number of monosaccharide units. So if you hydrolyze a polysaccharide, you will obtain that many monosaccharide units. We are going to deal with disaccharide. We are going to deal with glucose, fructose, these compounds, maltose, lactose. We are going to deal with these compounds. So next, we have told about sugar, non-sugar. Now, what are reducing sugars and non-reducing sugar? Reducing sugar means these carbohydrates are capable of reducing Fehling and Tollens solution or reagent. So if they are capable of reducing a Fehling or Tollens reagent, that means they have free aldehyde or non-bonded aldehyde and ketone linkages. Now you may think that why ketone? When it is a carbohydrate linkage, the behavior changes. And there are some compounds that are capable of reducing Fehling solution and Tollens reagent, and they are known as reducing sugar, and they are capable because they have a non-bonded aldehyde or ketone. If the aldehyde and ketone are chemically bonded, then they are actually non-reducing sugar. The first example that we are seeing over here of a monosaccharide is glucose. Glucose is a monosaccharide. It is obtained in ripe grapes and sweet fruit, Now, how is it obtained? Glucose is obtained from sucrose, which is known as cane sugar. Sucrose is also known as invert sugar, which itself is a disaccharide. Now, why it is known as invert sugar? Because sucrose itself is dextrorotatory. See, sucrose can be hydrolyzed. This is C12H22O11, which is sucrose, and it is dextrorotatory. But on hydrolysis in acidic medium using dilute HCl or dilute H2SO4, it produces equimolar mixture of glucose and fructose. That is 1:1 ratio of glucose and fructose with the same molecular formula C6H12O6. But different linkages. Glucose have an aldehyde linkage. Fructose has a ketone linkage. And to remember that glucose is dextrorotatory and fructose is levorotatory. The extent of levorotation of fructose is greater than the dextrorotation of glucose, for which the resultant solution behaves as levorotatory. So sucrose itself is dextrorotatory, but on hydrolysis, on account of production of fructose and glucose, and on account of greater levo-rotation of fructose than the dextro-rotation of glucose, the optical activity gets inverted. So this inversion of optical activity gives the name invert sugar to sucrose. So this is how you can also prepare glucose. Now regarding the structure of glucose, we have these points. We'll keep in mind these points, that the molecular formula of glucose is C6H12O6 and it is aldohexose. Why aldohexose? It means it has an aldehyde group and in total there are 6 carbon atoms. And it is under a category which is known as dextrose. That means dextro-rotatory sugar. And from what are the evidences of the structure of glucose? The structure of glucose can be written like this: CHO, CHOH whole 4, CH2OH. Now here we can see that the functional group CHO and glucose containing 6 carbon atoms, they have evidences from which you can say, like glucose on heating with HI, it forms N-hexane, normal hexane. So what all we can say? That since it is a normal hexane without any branching, that means there are 6 carbon atoms in glucose, which is a straight chain linkage. Next, glucose reacts with hydroxylamine, which is NH2OH, to form oxime. It reacts with HCN, hydrogen cyanide, to form cyanohydrin. From here we can conclude that it contains a carbonyl linkage. So this I have given it in a flowchart manner over here, that C6H12O6 is glucose. It reacts with HI in presence of heat to form N-hexane. From here we can conclude that there are 6 carbon atoms in a straight chain in the structure of glucose. And it reacts with NH2OH, which is hydroxylamine, to give you oxime, whose structure is derived in this manner: CH double bonded NOH. So obviously there was a CHO group. By the elimination of H2O, you have obtained this linkage. It reacts with HCN to give you cyanohydrin, which again has this type of structure. And from here you can conclude that glucose, the structure of glucose, has a carbonyl group in it. On reaction with bromine water, it undergoes mild oxidation to give you gluconic acid, whose structural formula is this. It has a COH in carbon number 1, followed by CHOH whole 4, followed by CH2OH. And from here we can say that, okay, if it is undergoing a mild oxidation and it doesn't need a very strong oxidation, then obviously the carbon which has formed COOH is a CHO. That means in the structure of glucose, carbon number 1 is an aldehyde linkage which has undergone oxidation to COOH in presence of bromine water. That is a mild oxidation. In presence of dilute HNO3, it undergoes strong oxidation and the compound obtained is saccharic acid, where we can see carbon number 1 and carbon number 6 both undergoes oxidation to give you COOH. Now, had the carbon number 6 been aldehyde, you would have obtained this type of structure with bromine water oxidation only. but you have got it by strong oxidation. That means that carbon number 6 is a 1 degree alcoholic OH. Moreover, I can say that if this gluconic acid having this structure is undergoing oxidation, it gives you saccharic acid where carbon number 1 and carbon number 6 is COOH, for which you can conclude that carbon number 1 is an aldehyde functional group which has undergone oxidation, mild oxidation by bromine water, and carbon number 6 is not an aldehyde linkage. It is obviously 1 degree alcoholic OH which has undergone oxidation. Next, then if you treat it with acetic anhydride, then you get a pentaacetate. And the structure of the pentaacetate is like this. That is CHOH. So the OH, H gets replaced by COCH3. And you get CHOCOCH3 whole 4 and CH2OCOCH3. So this shows that there were 5 OH groups in the structure of glucose which has given the pentaacetate. So these are the evidences of the structure of glucose. Now, moving on to the next part. It is saying that the Fischer structure. You know one thing, that the structure of glucose can be remembered by a mnemonic. The Fischer structure of glucose can be remembered by a mnemonic. So the structure of glucose is like this, right? It is having a CHO functional group. We have just now concluded it has a 5 OH, and here it is CHOH all 4, and the 6th carbon is a 1 degree alcoholic OH which is CH2OH. So this is the structure. Now this structure is having certain evidences which we have already discussed. Now the Fischer structure of glucose can be drawn by remembering a simple thing. This is a Fischer structure. Fischer is the name of the scientist. Remember, it is like a fishbone structure. Okay, so a fishbone structure, it is like this, that it is having CHO, so I can write CH double bonded O, and the last carbon, this is carbon number 6, 1, and the carbon number 6 can be written as CH2OH. This is the 6th carbon. And in between there are 2, 3, 4 and 5 carbon. Now it looks like a fishbone, but Fischer is the name of the scientist. Just now I have told you. Remember the right hand side configuration of this compound. Remember, if I use 2 numbers 1 and 2, 1 is H and 2 is OH. And remember, right hand side has 21, 22. 21, 22. If 2 is OH, then here it is OH. 1 is H. So 21. So 22. So OH and OH. So the opposite will be on the left hand side. Carbon number 2 has OH on the right hand side. So H. Here OH. Here H. And here H. So this is your Fischer structure of glucose. Now you can see it is given over here, Fischer structure. It is the open structure of glucose. And when you say gluconic acid, carbon number 1 changes to COOH, and the structure, rest of the structure, C2 to C6 remains the same. If you say saccharic acid, then carbon number 1 and carbon number 6 changes to COOH, rest of the structure remains the same. Glucose is named as D plus glucose. What is the significance of D? D means configuration, plus means optical rotation, and what type of optical rotation? It is dextrorotatory. Remember, deconfiguration, what does it mean? What is the meaning of this term, deconfiguration? Now, deconfiguration means the lowest asymmetric carbon has a configuration which is similar to D plus glyceraldehyde. So I am showing you this. What is the meaning of D plus glucose this side? So D plus glucose actually mean D is the configuration. I said the lowest asymmetric carbon. So lowest asymmetric means the last chiral carbon. That is carbon number 5. This is a chiral carbon. It has 4 different valency, CH, OH, CH2OH, and the rest of the part. So it has 4 different valency, and so carbon number 5, C5, is the lowest asymmetric carbon. It has the configuration of D plus glyceraldehyde. And what is D plus glyceraldehyde? It is the simplest form where you have the CHO as carbon number 1 and a CH2OH at carbon number 3. In between there is one carbon. So it is an aldose. We can see it is an aldose system and the simplest. And it has OH on the right hand side. And on the left hand side it has H. So the last chiral carbon or the lowest asymmetric carbon has OH on the right hand side and H on the left, which is similar to D plus glyceraldehyde, and hence the configuration is D. And plus is optical rotation, which means it is dextrorotatory. So this is the significance of D plus glucose. Next, moving on to this part, which says the 2 cyclic forms of glucose exist in equilibrium with the open chain structure. What are the 2 cyclic forms of glucose? They are alpha D glucose or alpha D plus glucose and beta D plus glucose, and they are known as the anomers of glucose. So we have to understand this. In order to understand this, we need to understand the cyclic structure of glucose, what it is. The cyclic structure of glucose is obtained by the nucleophilic attack of C5 oxygen with its lone pair to the electrophilic carbon. C double bonded O carbonyl linkage is a polar linkage and it is electrophilic in nature, and C1 having the main functional group for aldohexose, it is CHO. This C1 is known as anomeric carbon, and to this anomeric carbon it is a nucleophilic attack from the lone pair over oxygen at C5, and the anomeric carbon has C double bonded O. This double bonded O opens up and forms O minus, which holds the proton from C5 and becomes OH. So if I draw the Fischer structure of this, then how can I draw it? Let us see once. Otherwise, we will not understand. This is CH double bonded O. This is your last CH2OH. And this is your C2, C3, C4 and C5. This is 2, 1, 2 and 2. So this is H, OH, H and H. I said C5 oxygen has lone pair. With this lone pair, there is nucleophilic attack and O opens up as O minus, holding this H and forming OH. Now this carbon this was actually a chiral. Okay, it was not chiral. Why? Because it was having double bonded O. So obviously it was not chiral. Now, on account of this attack, it is becoming chiral and it has two groups. One is H, the other is OH. So this OH is if it is on the right hand side of carbon number 1, this C1 is known as anomeric carbon. It is known as anomeric carbon. And the last one, it is CH2OH. We are going to do the same thing, 2, 3, 4 and 5. So this is OH, H, OH. Remember that this H of C5 has gone as OH in C1, and there is this oxide linkage between carbon number 1 and carbon number 5, as if it is alkoxy group, and it is a hemiacetal form with OH also with this carbon, with OR also with this carbon, which is the anomeric carbon. And now let us get back to the structure, and now it is a chiral carbon. It has 4 different valency. So it is a chiral carbon. So H, OH, H, and this is H. Now this anomeric carbon, which is C1, has OH on the right hand side at C1 at anomeric carbon, and this configuration is known as alpha form. This isomer is known as alpha form. So this is alpha D plus glucose. But remember, this structure is same as a pyran linkage. Let us see this pyran linkage. Pyran compound, heterocyclic compound, it's pyran. 6-membered compound, 1, 2, 3, 4, 5 and 6, including oxygen. And when I am trying to draw the structure over here, we can see that it is C1, 2, 3, 4, 5 and 6. Don't think that I am giving the priority wise numbering. No, I'm just counting how many members are there in the ring. There are 6 members in the ring, including oxygen atom, and so the structure is similar to pyran structure, and so the name pyranose. So this isomer is known as alpha D plus glucopyranose, and now I am not going to name it as isomer. I will say it is an anomeric form, and so it is anomer. The other anomer will be having OH at C1 on the left hand side. So this is having OH on the left hand side, H on the right hand side, and rest of the structure remains the same. And always make the habit, ensure that you draw along with me. So this is what? This is OH, this is H, OH, and it has oxygen linkage, it's oxide, and here it is H, this is OH, this is H and H. OH on the left hand side at anomeric carbon, which is C1, and this is known as beta D plus glucopyranose. Whenever you are making it a ring structure, the hemiacetal form, use this pyranose term. So it is the Fischer representation, but these alpha and the beta forms are the anomeric forms of glucose. Next, we can see the cyclic structure of glucose. The 2 cyclic hemiacetal forms can be represented in the Haworth structure, and this Haworth structure has this type of form. Always remember how to draw the Haworth structure. The oxygen is linked with carbon number 1 and carbon number 5, C5 and C1. So to draw this structure, you always need to remember few things. That is, you have to, one structure I am showing for you, how to draw the Haworth structure. Use oxygen at this corner, make a 6-membered ring like this and draw along with me. This is your C1, this is your C5. Immediately draw the structure of C5. Make it the configuration as CH2OH over here and make it carbon number 6 and make this H. So draw the configuration at C5 and then make the groups at C1, at C2, C3 and C4. Remember, whichever was on the right hand side in the Fischer projection is below the plane in the Haworth structure. So whichever was on the right hand side in the Fischer structure is below the plane in the Haworth structure. So on the right hand side in Fischer, I said 21, 22. So it is what? OH. So this is carbon number 1. If I say OH on the right hand side, so obviously it is alpha form. Now here it starts to 1, 2, 2, 2, 1, 2 and till this you will stop. So the anomeric carbon C1 is having OH on the right hand side and so below the plane. So it is alpha D plus glucopyranose. This is glucopyranose. And now please see, this is H, H, OH and H. This is the Haworth structure. Now at C1, if this OH is above the plane, that is, it is on the left hand side in the Fischer projection, then it will be the structure of the beta form. So this is the Haworth structure, the cyclic structure of alpha D plus glucopyranose and beta D plus glucopyranose. So this is how you are going to draw the structure. Now one thing I said, the evidence that the cyclic structure of glucose exists. Number 1 is, it doesn't react with Schiff's base. So that means the aldehyde group is not remaining free. Next, the pentaacetate of glucose which you obtain by the reaction with acetic anhydride doesn't give reaction with NH2OH and doesn't produce oxim. The open structure reacts with NH2OH because in equilibrium your open structure also exists and the cyclic structure coexist. And the pentaacetate of glucose does not react with NH2OH to give you oxim. It doesn't form any addition product with sodium bisulfite, which is NaHSO3. And the crystalline structure of glucose, it has 2 forms, which is alpha and the beta, which are the anomeric forms with different optical rotation. 111 or 112 degree is the alpha and beta form is, this is the specific rotation and alpha form has a specific rotation of this, beta form has a specific rotation of this, but the aqueous solution of glucose has one specific rotation which is 52.4 degree. That means it comes to an equilibrium state and this specific, I mean the change in the specific rotation of glucose in its aqueous form is known as mutarotation. So these are the evidences of the cyclic structure of glucose.